So, I forgot what I call this. So, okay, so today we're going to do something like beyond the countable. Okay, so we're going to talk more about infinite sets. And this is on. Okay. And so let me just do kind of a recap of what happened. Okay. So, we're going to take S as set. And we had this thing. So this is the cardinality of S. Okay, and so this is defined to be the equivalence class of S under bijection. Okay, so so let me remind you how that worked. So that so two sets S and T, these things are the same, if and only if we said that S, and then I used double tildes or single, or I used something like this, okay, if and only if. Let me do this up here. So there exists a bijection F from S to T. Okay, so let me just make a remark about some other notation. So sometimes we write, S single tilde T, or like a little congruent symbol like that. Okay, and I actually, I wish I kind of take it back. I like this one the best. Okay, but all right. So same thing. It just means that they have the same cardinality. It means that there's a bijection. Yeah.
Some people use three horizontal lines.
Yeah, I think some people could use three horizontal lines. That would be something. Yeah, or that's another one that people could use too. Or they could do two lines here and equal sign over. That's another one, right? It is an equivalence relation. So we use our favorite equivalence relation symbol. Okay. I like this one because it really means like isomorphism of sets. So it means like that you're just going to be talking about sets. Well, it says that they're isomorphic. Okay. 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 So all right. And so then we had some other things. So for okay, so still doing the recap. So for this set, we had this abusive notation. Let me write it like this. Okay, where we took this set here, 1, 2, all the way up to n, and we just wrote that as n. Okay, so we treat this as like a cardinal number. It's really an equivalence class of sets, but we just write it as n. Okay, so we also had the other a notation that we used was that n sub n. So this was like 1, 2. We did it like this. Okay, so this was a notation that we used. And so let me just do some examples. So like this set, so like 1, 2. So this is 2, 0, 1. This is 2. We could do A, B. It doesn't matter what we put in there. It's just the size of the set that matters, right? And then you could go bigger Here, 1, 2, 3, 4. This is size 4, etc. Okay? So we just write the cardinalities like that. Okay? Okay? And then we had the countable infinity. So this was the cardinality of the natural numbers. And we gave this a name. So we do aleph naught. So there's a couple ways to write this. So this is the Hebrew letter. So aleph 0, aleph naught. So this is the Hebrew letter for A. So Hebrew is a lot like Greek. So there's like, aleph, bet, gimel, and then it goes on, right? So this is like A. It's like the first infinity, okay? Another way to do this is that it's like a line like this, and there's kind of two sticks coming out. So people write it like that sometimes, okay? All right. All right, so this is the countable infinity. And then what was the theorem we proved? We proved that, so we had a theorem, right, was that the rational numbers, right, had the same cardinality as the natural numbers. This thing. All right, and so that was really weird. So this is like, so I called this, I think, the first honeymoon theorem, right? So this is a theorem that came from this 1874 paper of Cantor. That's the same year he got married, right? And he's a terrible husband, and he went to go visit Dedekind on his honeymoon, okay, in Interlaken in Switzerland. All right, okay. So anyway, so that was the first theorem that he proved. And so I mentioned that, okay, so there's going to be different size infinities, okay? I made 3 outrageous claims, right? I said something like, there's different size infinities, and there's an infinite number of different size infinities. I said that the rational numbers have the same size infinity as this, and that the real numbers are different size infinity than the natural numbers. Okay? So I still need to explain to you why there's an infinite number of infinities, and that the real numbers that their infinity is a bigger infinity than this one. Yeah.
Does it have anything to do with like any two whole numbers in the real numbers? There's like an infinite amount of numbers between them.
It has nothing to do with that, because there's an infinite number of numbers in between any two numbers here, right? So you take any A and B here, right? That's what's shocking. That's the shocking part about this, is like between any two numbers here, there's an infinite number of numbers, right? Yet, we can still count them, right? That's the crazy part about that thing, is that we did this diagonalization thing where you write all the fractions, and then you do that little snake thing, and that's how you make the list of these things, okay? So yeah, this is shocking, right? Because between any two there are an infinite number of numbers, right? Between any two A and B, there's an infinite number of them. So it's like, it seems like this would be like somehow bigger than the natural numbers, right? That there's more of them. But you can actually set up a bijection between them. And remember, we're only talking about cardinality this in terms of bijection. You could always say that the natural numbers are smaller than this if you consider them as a subset. And then you can say that there's an element here that's not in here. But that's not what we're talking about. We're just talking about bijections. All right. Okay, so today, right? So today, I want to talk about this thing here. And let me say what this thing is, about this here. So this is the continuum. Okay, so I mean, it's almost like the rational numbers are a continuum, but here we call this the continuum. This is the cardinality of the real numbers. Okay? So we will show, so the spoiler is that this thing here is strictly bigger than this one. Okay? So there's another spoiler, I guess. So this is spoiler 1. Spoiler 2 is that, that this is the same cardinality as the power set of the natural numbers. Okay? We'll also show that there's an infinite number of natural numbers. So it's actually, so if you keep taking power sets, you'll be able to generate an infinite number of infinities. Okay? So you take a set, and then you'll show that the power set of a set is always going to have a bigger cardinality. All right. So I didn't talk about what this symbol meant. All right. So I'm going to define this first. Okay. So let's start with the ordering of the cardinal numbers. So okay. So let me give you a definition. So here's the definition. So we'll say, so let A and B be sets. Okay, we'll say that A is less than or equal to B if and only if, and this is the definition. So this is how I'm going to define. So today it's very important that I distinguish between these. So these are supposed to be sharp. This is like a less than or equal to sign. It's not a subset sign. Okay? So this is less than or equal to this if and only if there exists some C where C is a subset of B. And let me just chip into here a little bit. Okay? And C is the same cardinality as A. Okay, so this is saying that there's a subset of B that's the size of A. All right, so okay, so that looks like, meaning that it can be put into bijection with A. So that's what this thing here means. They have the same equivalence class, meaning that there exists a bijection between the two. All right. Okay, so I still didn't define the strict inequality. So how can I do that? So anytime I have one of these like less than or equal to's, I can define a strictly less than. So when you have a partial order, right? So this will be a partial order. How can I define a less than? So, okay, here's the first definition. The second definition is that A will be strictly less than B if and only if, by definition. Okay, how would I do that, guys? Yeah?
You just make C a proper subset of B?
No, you don't want to do that quite yet. So, so you can have two subsets like which are the same cardinality. You can have proper subsets which are the same cardinality. So I don't think you quite would. Yeah. But this is it has nothing to do with cardinality. Let me tell you that. It just has to do with relations. This thing like that. Yeah.
A and B are not equal.
Yeah. Exactly. So you say that A is less than or equal to B, and A is not equal to B. Okay. So that's how we define it. Like this. So that's the logical and. Okay? So you can always do that. You just say that, okay, it's a subset, but it's not equal. Or I mean, not subset. It's less than or equal to, but not equal to. Okay? It's, you can always do that type of thing. All right. So that's the ordering. That's how we order these things. All right. So let me prove a theorem. Let me start over on the other board. Well, let me state it over here. So theorem. So this is like the second honeymoon theorem. it says that that the cardinality of the real numbers is strictly bigger than the cardinality of the natural numbers, or that equivalently that R is uncountable. Right? So this is the theorem. So this is the second one second one coming from that paper in 1874. So that paper was has all the proofs, all the theorems about this stuff, or lots of them. So it's a big deal. Okay. And they didn't know. Yeah, I think when they were refereeing it, they didn't know what to do because it was just so weird. Yeah.
Is this also one of the crazy ones, or?
This is a crazy. This is one of the outrageous claims, right? So this is one of the crazy claims that I made, right? That there's different size infinities. Okay. So that in particular we have something that's already infinite, and this infinity is more infinity than this one, right? Yeah. And given that we already showed that the rational numbers are the same size, it's even more shocking, right? Because we already have something where between every 2 points there's an infinite number of points, like this one, right? But it's yeah. Okay. So let me tell you the proof idea. Okay. So the proof idea is as follows. Okay. So suppose someone in class comes and they're like, okay, I have a list. Okay, so suppose that we can generate some list of real numbers. Okay, so let me just do it like this. So prove first that this interval is uncountable. Okay, so this is the real numbers in between 0 and 1. Okay, and so here, so suppose someone comes with a list. We have some sequence. Okay, and so someone's like, okay, well, let's take these numbers, 1, 4, 1, 5. All right, so this is the truncation of pi. Right, so 0. So then we could do, let's see, what's another one that I could do? So you could do a third, right? Right, or you could do, so what is it? What is he? So 2.7182, yeah, 8182. Right? Okay, so then we could throw in some other numbers like 0.5, 0, 0, 0, 0, 0, 0, 0. Okay, so someone comes up to me and they say they have a list like this. Okay, they're like, okay, I counted. Here's my list. I've counted all the real numbers, right, in between 0 and 1, and I produced it. Okay, and so what we're going to do is we're going to shut this argument down by producing a number that's not in this list. Okay? And what we'll do is we take this digit, this digit, this digit, and the next one, so this digit, the fourth one, and we keep going like this, and we produce a new number. Okay? And we produce a new number by modifying each one of those digits. So we make a new number modifying the nth digit of the nth number. Okay, so here, let's just do it. So what I'll do is I'll just increment each one of these. So I'll do 0.2. So I just did this one. Then let's do 4, and then we'll do 9, and then we'll do 1, and then we'll keep going like this. Okay. So this is our new number. Okay, and so this new number will never appear in this list. Okay. Okay, so we made sure that it disagrees with every single number in the list. In particular, it'll disagree with the nth number in the nth list. You guys see that? Right, so it can't possibly appear. Yeah?
Why exactly can it not appear?
Well, okay, so what place would it appear at? The 101st place? If it appeared at the 101st place, I'll go look at the 101st thing down on this list. Then I'll go to the 101st digit here. And I'll know that those two numbers can't be the same because I modified this one in the 101st place, right? So it can't appear on the list. Because
the numbers that are constructing that number would not be in that sequence.
they cannot be in this sequence because I rigged it so that that thing disagrees with every single one of these numbers in a particular place. Does that make sense?
I guess.
So suppose it were to appear, like where could it appear hypothetically? Like the 1000th place? Or like the billionth or something?
But isn't it it's every number between 0 and 1, so isn't that technically between 0 and...
I'm supposing that you had this and I'm deriving a contradiction.
Okay, and so this is just a random sequence of...
I just wrote down a random sequence. So it's like if someone comes to me with some random sequence, right, then I'm gonna show you that there's no way that this thing can be that this sequence will be able to contain this particular number. So if you come at me with a sequence, I show you this thing.
Okay, and that sequence doesn't contain...
It does not contain that number.
Yeah, but it doesn't contain all the numbers between 0 and 1. It just happens to contain numbers that are between 0 and 1.
Yeah, this is okay. So it will never. So we're supposing that this sequence did, right? And I'm telling you that it's impossible. It's impossible because I produce a counterexample, right? Okay, so let me do this is the proof idea, and now let me do the proof, okay? And in the real proof, I'm gonna switch this sequence here to an arbitrary sequence, and instead of doing it in base 10, I'm gonna do it in base 2, okay? So let me just remind you, so that before the real proof, okay? So before doing the real proof, okay, so let me remind you so that there's this binary, so we can have base 2 numbers, right? So we can always write a given element x as a sum from, so like n is equal to negative, so 2 to the minus n bn like this. For n, bn will be an element of 0, 1, okay, up to infinity like this, okay? So we'll be able to write any number, so in the reals, can be written like this in base 2, right? And so this gives the decimal expansion, or a base 2, a binary number, let's say, let's say, so something like, so if x is less than 1, this gives something like point b1, b2, b3, etc. So this is just a string like this, okay? So I'm ignoring this thing where this sign here flips, and then you have positive things. So let me give you some examples, right? So like 2 in base 2. Okay, so the number, let's do the number, and the binary. Okay, so 2 could be like 1, 0.00 like this, okay? We could do 1, so this is 1.00 like this, okay? We could do a half, so this is 0.10, okay? So 1/4 is, so 0, you can do 0.1, so this is 0, 1. So this is like the halves place, this is the fourths place, and so on. So, etc. So 1/8 is 0.001 like this. Okay, do you guys get how this is working? Right? So it's just like this is the 2's place. This is the 1's place. Okay? So just like we have in usual decimal expansions. Okay? And then let me give some notation. So another notation. This is just temporary. This isn't like a thing. This is only for today, right? So if B is in 0, 1, so we'll let B bar, right, be 0 if B is equal to 1, and 1 if B is equal to 0. So it just flips. This just flips the bit. Okay? So bits are just a 0, 1. Okay. All right. So now, so I explained base 2. So the only reason I explained base 2 is just so I could do this in base 10 as well. I just wanted to make it a little cleaner. Okay. So let's do the proof of the uncountability of 0, 1. This interval. Okay, so suppose not, right? So we're supposing that this number 0, 1 is countable. Okay? So by being countable, this means that there exists a sequence that I could write down a sequence. So there's some sort of sequence that I could write down. So there exists, so we have some x1, x2, x3, x4, like this, and this continues on like this. And then I'm going to write this down in the binary expansion. So this is 0.b11, b12, b13, b14, and it goes on. Okay, so this is 0.b21, b22, b23, b24, and so on. And this is 0.b31, b32, b33, b34, and so on. Okay, and this is 0.b41, b42, b43, b44, and so on. Okay, and so this side also continues. Okay, so that means that we'll be able to write down a sequence, and that this is, so the claim is that someone has come to me, and they've come to me with this sequence that has all the real numbers here written in binary. So these are, okay? The fact that we're writing it in binary is not so important, okay? So I'm just going to proceed exactly like we did here, okay? So I'm going to produce the new number, right, that's not going to be in the sequence. And I'm going to do that by modifying the nth digit in the nth place, okay? So the number so 0.b11 bar, b22 bar, b33 bar, b44 bar, like this, right, disagrees. So IE is not equal to every number in this sequence. Okay? So why? This is because since, let me just do a comma, since it disagrees with xn in the nth place. Okay? And so this produces an example of a number that's not in the sequence. Okay? Hence, we have a contradiction. Does that make sense? Yeah.
Can you just show how like the bit
Flips, like just like a small example. I'm just confused.
So yeah, so let's like write, let me just write down a random example, okay? So let me write down this idea again, and then I'll show you how to do the uncountability of R, the full R, okay? So, so here's the idea. So let's do, I'm just writing random things down. Oh, I already, that one didn't appear yet. Okay, so the idea here is that so this is like if someone comes at me with this one here, so what I'll do is I'll write down the number, so the new number, so this is continues. So it'll be 0.1, so I'm doing these guys here. Okay, so I flip this one, flip this one, flip this one, flip this one. Like so, like that, okay? And so if I continue in this way, it would be a new sequence here that doesn't appear in this anywhere, a new element that doesn't appear anywhere in the sequence. Yeah?
In base 10, do 9s turn back to zeros?
Yeah, you just have to, you can do, in base 10 you can do whatever choice you want, right? So you can, just as long as you change it, as long as it's different, you're good, right? Yeah, yeah.
This is the modification, that like method that we're using instead of just adding one from the first example.
Yeah, instead of just adding one. But the thing is that if you do 9, then you have to round, or like, you know, instead of adding one, you just have to modify it, right? And there's only one, the only reason I did base 2 is because there's only one way to modify it, and it looks prettier, maybe, you know? It doesn't matter so much, okay? All that matters is that you take your sequence like this, and then you just modify it, right? Okay. Other questions? These are good questions. I was going to do the...
This just shows that it's uncountable.
Yeah, this shows that it's uncountable, right? It's uncountable because, you know, anytime you have a sequence, right, you produce one that's not in the sequence, right? So it's like a contradiction. So if anyone comes at me, they're like, hey, I have this sequence, right? You shut down the sequence in this way, and you show that they're wrong because here's my number that's not in your list. Yeah. So when they come at you, they're like, oh, I got this computer program, right? And I've counted all the real numbers, and you're like, you're an idiot. And then you show them that this is impossible to do, right? Okay. All right. So that's weird, right? So this is a very strange fact. It's like, okay, so we have the rational numbers, and we have the real numbers. And so this kind of says that most numbers are not rational, okay? Okay? And actually, it's even worse than that. So like, it turns out that there's these things called algebraic numbers. These are things that satisfy there's zeros of polynomials with q coefficients. So like square root of 2 is the solution of like x squared minus 2. So that's an algebraic number, right? So those numbers themselves are countable. So like all those irrational numbers like square root of 2, square root of 3, you know, things like that, those are also countable, it turns out, right? So it turns out that the bulk of numbers are like pi and e and things that are not algebraic. And it's very strange though, because like we work a lot with the algebraic things, but it turns out that like most, uncountably many of them are not like this, you know? Like these are just make up a very small piece of what's the actual numbers are. Okay, let me just say quickly how to go from the 0, 1 to the full thing. So let me just say that what we did. So we proved that this thing here is uncountable. Okay, so to prove R is uncountable. Well, it's pretty believable, right? Because this is a subset of this, right? But these two things have the same cardinality. So recall that this thing here is the same thing as this interval here. Okay, so the picture for this was this like doodle that we did, right? So we had, so here was the real line, right? Here was 0, and we drew like here's -1 and 1, and then we had, let me make this completely through here. Okay, so I did another copy of the real line, but I just displaced it by in the xy plane by 1 up here. Okay, and so we had a function that went from this semicircle to this line, and the function from the semicircle takes a point here. It draws a line through this thing, and then it maps it to this point. So this thing maps to this thing. So that shows that the semicircle and the real line are in bijection. Okay, this is the open semicircle. Okay, and then to get a bijection between the semicircle and the interval, -1 to 1, we do this thing. Oh, sorry, I'm just doing -1 to 1. Right? To show that the semicircle was in bijection with this interval, right? We just kind of like take this point here, and we project it down to that line. Okay? All right. And then, so what you need to do, what remains to be done, is to show that this thing is the same thing as the other interval. So we can show that -1, 1 is the same thing as 0, 1, like this. Okay? So these two things have the same cardinality, right? Meaning that there's a bijection between them. Okay? And so to do that, you just use a line. All right, and what do I mean by this? So let me just draw the graph real quick. Here's x, here's y. And so we want to map, let's say, 0, 1. So 0, 1 to the interval -1 to 1. So -1 to 1, right? And so what you do is you just take these things, and then you take so this is supposed to, it's supposed to intersect halfway through. Okay? And so you just constructed this line like this that maps this interval to this whole thing. Okay? So you have 2 points, you make a line, right? And then that'll give you the function that maps this one to this one.
Will it always go through the point 1/2? Is that like our anchor point, just like with the circle, it was the center of the circle?
I mean, this one will go through 1/2, yeah. It's just from the fact that, I mean, there's other bijections. This isn't the unique bijection.
Will all lines in this one go through that 1/2, and that's how we cover it, or no? So in other words, is that the same anchor point like it was with your circle, and then we use one more point?
No, I'm not sure how you're thinking about it, but it's probably what you're saying is a valid way of thinking about it. And there's many ways to think about this. Okay, so like remember, if you go and ask someone how to think about something and your answer is different, right? You're okay, right? Yeah, and so I imagine what you're saying is probably correct, right? I'm not exactly sure, but we can talk about it after. Okay, so all right, so that shows that the real numbers are uncountable. Okay, so all right, so now I need to show you the other outrageous claim, right? Well, the other outrageous claim. So we've covered that the rational numbers are countable. The real numbers are uncountable. Anytime someone shows you a list, the list is incomplete, right? And now I'm going to show you that there's an infinite number of infinities. Okay, so what's beyond? So we have this countable infinity, we have this uncountable infinity, this real numbers. Is there something beyond that? Okay, can we go bigger? Right? Yes, you can go bigger. You can always make a bigger infinity. All right. So beyond. Okay, so beyond this continuum. There's more infinities, all right? So let me tell you the theorem, and then I'll tell you how to apply it. Okay, so theorem. So let X be a set. So the theorem is that the power set of x, the cardinality of the power set, is strictly bigger than the absolute value of x. Okay, so this was, I think this also appeared in this paper. I would need to check on it. So, okay. So, but, so yeah, so we have this, so we have the countable infinity, and so in our application, so this means to get bigger infinities, we can take x to be equal to the real numbers, right? And so let me just give you a spoiler here. So it turns out that the cardinality of the power set of the natural numbers is the same thing as the cardinality of the real numbers. Okay? So we'll talk about this in a bit. But first, I want to just kind of show you how to produce new more infinities. Okay? So here, so note now. Sequence of infinite cardinals. Okay, so we have the countable cardinal, right? And then we have this power set of the cardinals, and then we can take the power set of the power set, power set of the power set of the natural numbers, and then you can just continue this process, right, to get tons of infinities. So you just take the power set of the power set, and then you can keep going. And so this produces a countable sequence of infinities, right? This one's an uncountable one, and then it goes beyond uncountable, right? So you could, ask other questions. Okay? So let's prove. Let's prove this. Right? So let's prove this theorem. Okay, so the proof. Okay, any questions before I get into this? All right. So what do you guys think I do here?
Just show that the power set can't be put in bijection with the
Yeah, that's exactly what we have to show, right? So what should I do? Like, how do I start? Suppose not, right? Let's do that. Suppose not, and then I'll show that it's nonsense. Suppose not, right? So if f, so this means that we suppose that there is a bijection from x into the power set of x. Okay? So this is an f, all right? So I'm going to go this way. I think it's clear that this one's at least as big as this one, right? Because you have all the singleton subsets. You just throw curly braces around a single thing. Okay? But let's go the other way, right? So let's suppose not, and suppose that we have some bijection between x and the power set of x. Okay? All right. All right, and so this is the trick. Here's the trick. Okay? So the trick is we're going to consider a certain set. Okay? So we consider the following set, y. All right? Y, it's going to be a subset of x. It's the set of x. Let's call it a in x, because I don't want to do big and little letters. So a in x such that a is not an element of f of a. Okay? So this now we're using the fact that this is a map between the set and the power set. So it only makes sense to talk about this relationship of A being an element of f of A if f of A is some sort of set. Okay, so this is a set that has to do with A. You know, so like A maps to some set. Okay, so we can consider this set. Okay, since f is a bijection by hypothesis, right? We're supposing that this is true. There exists some y such that f of y is equal to y, because this is one of the things in the power set. It's a subset of x, right? And we suppose that it's a bijection, so there should be something that maps to it. All right? All right. So let's look at this. Okay, so is y an if y is an element of f of y, which is by definition y, right? Well, y is what? It's a set of a's such that a is not an element of f of a. Then y is not an element of f of y by the definition of y. Okay, so that's a contradiction. So y can't be an element of f of y. Okay? So if y is not an element of f of y, right, then what do we have? So then, by definition, y is an element of y, which is f of y, by the definition of y. Of this big Y, right? So this is also a contradiction. Right? So we can't have either, right? So this is nonsense, right? So this gives so y can't be in this y, and it can't be in the complement of y. So it's not a thing. Yeah?
So you have like an element of a set that's all the things that aren't in f of a, and then because it's not in that set, it's in that set y?
Yeah, so you have you had a set, and you made the set of things A such that A is not in so every A maps to some subset of X, okay? And so you make this relationship where you say, okay, I'm going to make this set, right, where it's a set of A's such that they're not in the set that A mapped to, okay? And since you constructed this, you know that, okay, you have a bijection, so this is mapped to something maps to this guy, right? And you either have that y should be an element of this, or y should not be an element of this guy, right? Because these two things are the complement of, the union of, one of these two things should be true, okay? But whenever you assume one of them, you get a contradiction. So the whole thing's nonsense, okay? Which means that this function can't exist, right? It's kind of tricky thinking about these things because we're talking about something that doesn't exist, okay? So to try and like come up with an example or something in your head is like, doesn't make sense because it doesn't exist, okay? So like this, we showed that it's impossible for this to exist. Yeah?
So it's kind of like the heads I win, tails you lose sort of thing?
Yeah. I don't know.
We're like, I don't know, it's weird to think about. Where you have like you have a group of things that like all don't belong, but they like belong because they belong to like the set of things that
Yeah. It's exactly like that. I had to think about it. Yeah. It's exactly like yeah. It's yeah. I mean, you just break it into cases where both cases are nonsense. Yeah.